Welcome to our end of the semester talk about a project physics-based graph layers in hyperbolic space. I'm Anna. Above me you can see David. And we want to give you a quick update about what we did so far during our project, and especially since the middle of semester talk. So first, to give you a quick recap about what we're doing, we want to model graphs as physical systems in hyperbolic space. Hyperbolic space meaning we want to represent it on a Poincare disk. We want to model the graphs by considering the nodes as electrical charges that repel each other and the edges of the graph as springs that pull the nodes together. To avoid our graph flying around somewhere, we also added gravity to the center point of the Poincare disk that pulls it somewhat towards the middle. So what we did since the mid-semester presentation, we implemented the hyperbolic force atlas 2 algorithm that calculates all the previously mentioned forces on each node and under some strategies applies them to the nodes until it hopefully reaches an equilibrium where the graph then stays. We also implemented a way to display our graphs, so you can see what the graphs look like, and you can also get GIFs of your graph during the assembling process, where you can see how the graph assembles itself on the Poincare disk towards its equilibrium. In case your graph gets stuck, which happens sometimes, we also implemented a way to move the nodes by clicks so that you can catch your nodes if they are wandering off. Maybe you want to see an example of a graph. Here you can see the square tail graph. I think we wait one repetition. You can see it starts in the middle by a random layout. It wobbles around a little, it pulls itself around the Poincare disk, and then it reaches its equilibrium state right below the center point. So now David will explain to you what our problems and issues are.
Yeah, so we've got a long way, but there are still some issues. For example, the algorithm is prone to numerical errors sometimes. Sometimes you just see that a point escapes the Poincare disk somehow by the margin. And second point is it's sensitive to the choice of constants. So, for example, the choice of gravitational constant or the spin constant, depending on the graph. And we also have a long computation time, and this is an issue we have to fix to lay out larger graphs. So in the future, we have to try to solve the problems, implement the strategies to reduce numerical error. We want to set up a user interface where you can set up the constants nicely with a button or something like that. And we also want to apply strategies to reduce runtime. Okay, so maybe to finish the presentation, we can show another example of our algorithm. And here you can see a tree-like graph. In the beginning, there's this random process, and then it's getting layouted by the force atlas 2 algorithm, and you can see slowly it gets to a state where it's staying the same. It's still wandering around. But now it's kind of stable. You can see the shape of the tree. And well, it's now walking around a bit, but I think this is a good example. And thank you for listening, and have a nice day.